Okay, let's continue with our topic. So we've already seen directivity, and now we're gonna talk a little bit more, and hopefully we would be able to understand another important quantity, which is the gain of the antenna. So to review what we mentioned was that d theta and phi, which was the directivity of the antenna, was essentially a ratio of the radiation intensity that we had divided by the radiation intensity of an isotropic source, assuming that isotropic source radiates the same amount of power as the antenna. So if I have an antenna here, so this is, let's say this is the input port of the antenna, and from here I go to a space, that's my P radiated. So I need to have the radiation intensity of an isotropic source, assuming that I'm radiating the total power radiated by the antenna. So, and that would be P radiated divided by 4 pi, which eventually becomes 4 pi u theta and phi divided by P rad. So that was a definition of directivity that we had, and based on that, we could calculate directivity. But there is one thing about this that might not be completely comfortable. And the reason is, if you look at these P radiated, you need to know the total power radiated by your antenna. And how would you know the total power radiated by your antenna? Think about measurements. If you go by math, it's probably easy to calculate it, but think about measurements. How can you find the total power radiated by your antenna? You essentially need to go around the antenna in the 3D space and measure the points around the antenna and sum them to have the total power radiated. So total power radiated is not something that you can take it for granted. So it would be nice if we could have another quantity that's related to directivity, but perhaps it's easier in terms of this power. Now, what is easier is essentially the power that we're giving to the antenna, because remember, this side is a space, this side is your circuit. So we're bringing power to the antenna with a transmission line, and this power would be the power that's going to go into the antenna. So this is, let's call it the P that's accepted by the antenna. So if you know how much power you have in your transmission line, remember that gamma square of that reflection coefficient square is going to reflect back, and the rest is going to go through, which would be 1 minus gamma square times the power that you are providing to the antenna. So at this point, you can easily measure the power that the antenna accepts. And the power that the antenna accepts is not necessarily equal to the power that it radiates, because then your antenna may have some loss due to non-ideal conductor, non-ideal dielectric. So this is very straightforward to measure. So we just need to know the power in your transmission line. We know the reflection coefficient. And remember, we always know the reflection coefficient because we know the impedance of the antenna. So reflection coefficient, if you remember, was ZA minus Z naught, ZA plus Z naught. That was the reflection coefficient. So you see, as soon as you think about measurement, then you understand why perhaps we want to have another definition, which we call gain of the antenna. And don't confuse that with the gain of amplifier, which is an active, things like that. Still, in most cases, actually everywhere in our course, we assume antenna is a passive structure. So we're not increasing the level of power. We're just accentuating power in one direction and therefore suppressing it on other direction. So the name gain shouldn't be confusing here. So gain of the antenna is exactly like directivity. So you have u theta and phi in the numerator. That's the radiation intensity of your antenna. But then in the denominator, instead of using radiated power as the reference, you're going to be using the accepted power by the antenna as your reference. So you essentially going to say what would be the radiation intensity of an isotropic source, assuming that it radiates, assuming that the total power is P accepted. So let me repeat that. You're going to say radiation intensity of your antenna divided by radiation intensity of an isotropic source, assuming that total power is P accepted, not P radiated. Then you're going to write P accepted divided by 4 pi. And that's going to be 4 pi u theta and phi divided by P accepted. So this is really the distinction between the gain and directivity. So as you see here, if you compare this with that, you see that the main difference here is that this is total power radiated, this is the accepted power by the antenna. Okay, so we have now our directivity and gain, and one question could be, what is the relation between directivity and gain? The relation is essentially the relation between accepted and P radiated. I want to remind you about something that we defined earlier in the course, which was radiation efficiency of the antenna, ECD, which was essentially the ratio between radiation resistance divided by total resistance of the antenna, radiation resistance plus RL. Remember, this was radiation, this was lost within the structure. So if you go from the port of the antenna to the total radiated power, this P accepted is going to go through loss, and then it's going to radiate. So in these cases, what's going to happen is that this RL is going to have its own effect, because RL is the source of loss when you go from here to radiation. So immediately you see that this radiation efficiency is something that's connect P radiated to P accepted. So in fact, you can say P radiated by the antenna is equal to radiation efficiency times P accepted. So if radiation efficiency is 100%, in other words, if radiation efficiency is 1, then P radiated is equal to P accepted. And if that happens, directivity and gain are the same thing. But now, if efficiency is, for example, 40%, then of course, P radiated would be smaller than P accepted. And if you look at, because these are in the denominator, directivity is going to be more than gain. So it depends which one you're more comfortable with. Usually gain is more practical, because if you have loss in your antenna, you want to be able to see that. So it's often better to have the reference as P accepted than just P radiated. Because remember, let me make an example here. Imagine you have, I'm going to go an extreme case. You bring maybe, let's say, for example, 1 watt to the antenna by transmission line, because you have some reflection. Not all of it is going to go to the antenna. Let's say 0.9 watt is going to go to the antenna. So this is P accepted, right? And this is P accepted, but then imagine you have a very lossy structure. So this 0.9 watt, when it's radiating, P radiated, total power radiated, becomes only, for example, 0.1 watt. So now if you go by directivity definition doesn't show you that you had a very lossy structure and you ended up with 0.1 watt. It just says, what is your radiation intensity? Divide that by the radiation intensity of an isotropic antenna, assuming that isotropic radiates 0.1 watt. So you essentially get a very good number. But your antenna is not very good. Your antenna is very lossy. So, so, but if you go to the gain definition, the story is different, because the thing that's going to happen is that you are still going to have your radiation intensity, and your radiation intensity is not very good because you radiate less power because it's very lossy. So this number is not very good. U theta phi is a small. I'm using this arrow to show this is a small. So this is a small, but then you the power that your antenna accepted is not a small, it's actually large. So this is a small, this is large, so you end up with low gain. That tells you that your antenna doesn't function well. So to do the same thing for directivity, in directivity, of course, numerator is the same thing. So numerator is a small, but then remember, because of loss, your radiated power is also a small. So this one is also a small. So both of them are small, so they cancel the effect of each other. But in the gain, that doesn't happen. So you see the effect of the structure of the antenna in the gain. So this is one thing to keep in mind. The other thing is that we have another definition for gain, which is called absolute gain. And in the case of absolute gain, we're going to change the reference to this power. So instead of going with 0.9 watt, we're going to go with this one, for example. And the nice thing about that is that it not only includes the loss of the antenna structure, it also affects how bad is your mismatch here. So it incorporates the effective reflection coefficient as well. I mean, if you're using the simulation software in this course, you see that you can plot directivity, you can plot gain, you can plot absolute gain. So all of them are possible. So the other thing about directivity that you need to understand is that directivity, if I use dimensionless, is always greater than 1, because directivity of 1 is for isotropic antenna that doesn't exist. So the maximum directivity of any antenna would be greater than 1. By the way, when I'm saying directivity and I give one number, I'm essentially meaning maximum directivity. So maximum directivity of any antenna is greater than 1. Or if I say it in dB, would be greater than 0 dB. Any antenna, it doesn't matter. But for gain is a different story. Gain can be smaller than 1 because gain also includes the loss. Let me make an example, for example. So imagine, for example, I have an antenna with a directivity of 1.5. So as soon as I say directivity of 1.5, I'm talking about maximum directivity, D naught. So I'm assuming this U here is U max. So 4 pi U max divided by P rad. So this is directivity is 1.5 dimensionless. And let's assume the ECD is 40%. So now I'm asking you what is gain, maximum gain in this case. So first of all, notice that directivity is greater than 1, dimensionless. You can, of course, convert it to dB by saying 10 log 10 1.5, which should be about 1.76. So 1.76 dB. And as we mentioned, we could also write it as dBi. They're the same thing in this case. So we're comparing it with an isotropic antenna. So your efficiency is 40%. Now, remember that when you have efficiency of 40%, it's going to affect the gain. Now, we already mentioned that P rad is ECDP accepted. So let's try to use this to connect gain with directivity. So remember, gain is 4 pi U theta phi divided by P accepted by the antenna. Now, I know that P accepted is P rad divided by ECD, so I'm just going to remove that, and I'm going to write P rad divided by ECD. So I'm going to take ECD to the numerator, so that's going to be like this. And you already know this is directivity. So gain would be therefore ECD times directivity. So this is going to connect gain to directivity for me. And remember, this is dimensionless. If you have dB, then you essentially, it's going to be addition. So gain would be ECD times D. Remember this. And therefore, now we can use these two to find gain. Gain becomes 40% is 0.4 times 1.5. So that would be our gain, which in this case becomes 0.6. And if I take the dB, it's going to be 10 log base 10.6, and that's minus 2.2 dBi or dB. So if you look at here, first of all, as you remember, I said directivity is always greater than 1 because there is no loss involved. But because loss is involved, G gain can be smaller than 1.6. Now, if I translate what I said into dB, I should say directivity in dB is always greater than 0. Is always greater than 0 dB. But gain, that's not the case. Look at gain in dB, it's minus 2.2 dBi. So gain is in fact negative in this case. So you can so appreciate the difference between these two quantities. Okay, let us now consider one example and then try to solve this using an example. So let me start my example with giving a radiation intensity and then asking you to find the directivity associated by that. So the radiation intensity that I have in mind for this example is equal to A naught. A naught is just a constant here, and it's sine 2 theta. So that's my radiation intensity. So I'll give you radiation intensity, and I'm asking you to find the directivity of this antenna. So when it comes to this radiation intensity, again, I want you to see that radiation intensity that I give you does not have any phi dependency. There is no phi here. So that means if I go around the antenna, for example, in the XY plane, I should see the same thing. So this looks like, again, a dipole antenna. When you go around it, you don't see difference. And then if for theta equals 0 and theta equals 180 along the axis, there is no radiation intensity. So that essentially means null in those directions. So you could get some idea about the antenna. But we want to understand how does this antenna compare to the hypothetical isotropic antenna. That's the purpose. Now, to do that, I need to go for the definition of directivity. So definition of directivity tell me I need to compare my radiation intensity with the radiation intensity of an isotropic antenna, assuming that the isotropic antenna radiates the total radiated power by the antenna. If it does that, so its radiation intensity becomes P rad divided by 4 pi, and therefore I get 4 pi u theta phi divided by P rad. So remember, this was the radiation intensity of an isotropic antenna, assuming that it radiates P rad. And the reason I divide by 4 pi, because we have a sphere, complete sphere is in total 4 pi stradian. So that's why I divide it by 4 pi here. Now, so essentially directivity is there. I already know u, theta, and phi. I can plug it here. The only thing I need to find is P rad, the total power radiated. How do I find that? So I'm just going to say P rad is equal to, if you remember, you need to sum up the power in all the cones around the antenna, which is the integration of u, theta, and phi over d omega, which is going to be a naught sine 2 theta, which is this one, and then d omega is sine theta, d theta, d phi. So this is your d omega. And remember, phi goes from 0 to 2 pi, and theta goes from 0 to pi. So if I have my 3D coordinate, this is variation of phi, 0 to 2 pi, and this is the variation of theta going from 0 here to theta equal pi here. And this is phi equal 0 to phi equal 2 pi. So I need to integrate over the whole sphere. And you see immediately, I mean, you might say, okay, why this is just 0 to 2 pi, why you don't come back again? Because phi equals 0 is here, so I'm covering half of the sphere, and because with the phi from here to here, I'm coming to the other side, I'm covering the other part of the sphere too, so this one doesn't need to go all the way back, so it could be 0 to pi. That's the standard of a spherical coordinate. Now, so essentially you need to calculate this integration because there is no phi dependency in the integrand. You can essentially factor it out. Integral of 0 to 2 pi d phi is 2 pi. So, and you can bring a naught out, and you're essentially going to have sine cube theta d theta 0 to pi. So you need to integrate sine cube theta. And to do that, we know that sine 3 theta is 3 sine theta minus 4 sine cube theta. So here we have sine cube under the integrand. Therefore, sine cube theta becomes 3 sine theta minus sine 3 theta divided by 4. So this is our sine cube theta. So I'm going to substitute this instead of sine cube. So I'm going to have 2 pi a naught 3 sine theta minus sine 3 theta divided by 4 from 0 to pi d theta. And that's going to give me 2 pi a naught. That's going to give me minus 3 by 4 cos theta and minus plus 1 divided by 12 cos 3 theta. Okay, so if I calculate that, now this is going to be 2 pi a naught. This is going to be cos pi minus cos 0. That's going to be minus 2. And this is the same thing here. So this is going to be minus 2. 6 divided by 4. And this is going to be again minus 2 times 1, 12. That would be minus 1 divided by 6. And that's going to make it 2 pi a naught 12, 18 minus 2. And that would be 2 pi a naught 18 minus 2 would be 16. And I'm going to get 4 divided by 3. So I have 4 divided by 3. Let me double check. So I guess it's correct. So that's my total radiated power, 2 pi a naught 4 divided by 3. Again, I want to remind you that, look, u, theta, and phi was a function of theta. Total power does not depend on theta because you integrate. So that's your total power. Therefore, you can find your directivity as d theta and phi equal 4 pi, that's 4 pi, u theta and phi, a naught sine 2 theta divided by total power radiated, which is this one, 2 pi A naught 4 divided by 3. Now, what's going to happen? That's the most important thing here, that A naught and A naught cancel. This is very important because remember, A naught has to do with how much power you're giving to the antenna. We don't want our quantity to depend on the watt that we're giving to the antenna. We want the performance of the antenna for any power. So A naught has to do with the actual power that you're giving to the antenna. Is it 1 watt? Is it 10 watt? 100 watt? So as soon as you do this ratio, you cancel the effect of the watt that you're giving. So it's the general performance. So if I say my maximum directivity is 3 dB, that means I'm 3 dB better than isotropic antenna for any amount of power. Of course, as long as antenna can handle that power. But this is very important that A naught and A naught cancel. So now you're not dependent on the value of the power that you're giving to the antenna. Remember, in radiation pattern, if you give, for example, 1 watt to the antenna and you measure the field value, so you get one field value. If you change the power that you're giving to the antenna, you get another thing. And that's why that number is not really meaningful. That's why we normalize it. But here, because of this ratio, this nice thing happens. And then 2 pi and this cancel. You get 2 here. And then, therefore, you get 6 divided by 4. You get 6 divided by 4 sine 2 theta, or 3 divided by 2, which is 1.5 sine 2 theta. So this is our directivity calculation. Now, if I just ask you what is the directivity of this antenna, you usually don't say 1.5 sine 2 theta, although that's important. You usually say 1.5. You report the maximum directivity. And why 1.5 is maximum? Because maximum value of sine of theta is 1 at theta equal 90 in this case. So maximum directivity is 1.5. That means this antenna, independent of the power that you're giving to it, is going to perform 1.5 times better than isotropic antenna at theta equal 90 degree. And this comes with another things, that because it performed 1.5 times better in theta equal 90, then at theta equal 0, it does not even radiate in that direction. So that becomes our directivity. Now, if this is the directivity, and now I'll tell you that the radiation efficiency of the antenna is 0.9 or 90%, then you can also find gain. So if I say, okay, look, ECD is 90%, then you would say, okay, therefore my gain is radiation efficiency times directivity, and that's going to bring me to 0.9 times 1.5 sine 2 theta. So as you see, gain would be smaller because radiation efficiency is not 100%. So that's one thing that you could do with that. The other thing that you could do with this value is to find the half power beamwidth of your antenna. So to find the half power beamwidth of your antenna, what you need to do is that you essentially want to find the theta at which power is half of the maximum. So if you look at directivity, the maximum that you have is 1.5. And remember, directivity has to do with power. So it's not like field pattern that you find 1 divided by a square root of 2. Essentially, it's half. And your maximum is 1.5. So half of that would be half of 1.5, which is half of 3 divided by 2, 3 divided by 4. So you're essentially looking for theta at which you have the value of directivity is 3 divided by 4. So this is this is what we are looking for. So we can try that. So we know our directivity is 1.5 sine 2 theta. We want this to be 3 divided by 4, or let me write it completely. We want it to be half of 1.5 because 1.5 was maximum. We want half of it, half power beamwidth. So 1.5 and 1.5 cancel. So sine 2 theta becomes half. Now, how many answers we have for this one? So remember, if that happens, that essentially means sine theta is 1 divided by a square root of 2. You can have plus minus here. Because I'm considering theta from 0 to 180, the negative is not relevant here because when theta varies from 0 to 180, sine is always positive. So if I have sine theta equal 1 divided by a square root of 2, then I have two solutions for that within 0 to 180. One of them is theta equal 45 degrees. The other one is the same thing, but this time 180 degrees minus 45 degrees, which is 135 degrees. So for both of them, I get 1 divided by a square root of 2. To remind you of that, let's consider the sine axis. This is my sine. So if you are 45, this is the sine. If you are 135, this is the sine. So this is 45 and this is 135. So for both of them, the sine value stays the same. So that's why I have two solutions. Okay, now I have 45 and 135. Therefore, my half power beamwidth is the angular separation between these two, which is 135 degrees minus 45 degrees, and that's going to bring it to 90 degrees half power beamwidth. So if I plot this directivity, I'm essentially having something like this. And the maximum value is 1.5. And then this is theta, sorry, this is z axis. So now this is theta equal 45. So at this point, at theta equal 45, I'm half of 1.5. Then I'll go to 135 theta. Again, I'm half of 1.5. And then the angular separation between these two lines is this angle here. And this angle, of course, would be 135 minus 45, which is 90 degrees. Okay, I hope this example helped you to better understand directivity and gain.